Yeah, good afternoon, ladies and gentlemen. We'll start our session on condition monitoring using SVM as a tool. So if you see the block diagram view of the electric vehicle, the power side of it looks like that. The grid is here in one side. Then on this side, you are having the grid, having a AC to DC rectifier, and then it charges a battery. And battery itself, you are having a low voltage battery and a high voltage battery, between which you are having a DC-DC converter, because any of one voltage level will be available out of the rectifier. And then you are having a DC to AC converter to drive the motor. So the mechanical power will be delivered by the motor. So this is the power view of the electric vehicle. So you can see there is a lot of power electronics in the modern electric vehicle. Not only in electric vehicle, if you see your home also, or the classroom in which you are sitting, everywhere you can see the impact of power electronics. You cannot lead a life, or you cannot complete a day without having at least 2-3 power electronic equipments used. You see, for example, if you want to charge your mobile phone, you need a AC-DC converter and a DC-DC converter, right? So that's a power electronic solution. If you want to see this lecture class, you need a television or a laptop or a desktop. All this needs a power electronic solution. For example, in a television, you are first converting the AC 230 volt single phase AC to DC, which is again converted to various levels of DC using a DC-DC converter. Or if you take the laptop, you are having a battery which is already charged by from the mains. Now it needs another DC-DC converter for getting different levels of DC voltages inside the laptop. The digital system needs some 3.3 volt. The motor for the drive needs 12 volts. Like that. So many different levels of DC voltages are required even inside a laptop, which is derived using a power electronic solution. So everywhere, or if you see the light you having today, you are having LED light. So you see the LED is not working in AC directly. It needs a AC to DC converter, which converts the available AC to a high voltage DC, and then a DC-DC converter to get your required level of voltage, maybe 1.5 voltage or 2 volt. That's the kind of DC voltage your load is looking for, the LED light is looking for. Same way, if you take the modern fan, it's made from BLDC motor. Nobody now uses a induction motor. So BLDC motor is again working from a inverter, right? So that is driven by a power electronic converter. So everywhere, whatever you see, you take the case of a refrigerator, you take the case of a modern air conditioner, all of them are working from a power electronic solution. So the impact of power electronics is very vast today. Everybody uses power electronic converters in one form or another every day. Okay, so that is the scenario. So power electronics playing an increasingly important role in not only in automobiles, in everyday life, all of us. Okay, and then is being used to enhance the output power capability. Basically, the role of power electronics is to enhance the output power capability, efficiency of the power generation, improve the quality of the power. When I tell the quality of power, it is the correct amplitude, correct frequency, everything. Okay, so that also is ensured using a power electronic solution. So power electronics also an enabling technology for wide range of improved functions. Whenever you are having a improved technology, the requirement also increases. Say, we are having a luxurious car. You don't want the manual intervention. You want everything to happen automatically. I want to attend my call when I am driving. For that, I need a Wi-Fi enabled or Bluetooth enabled mobile phone connectivity to my car communication system, right? So that's what. So that was unimaginable some 5 years back. So that's what I have told you. With improvement in technology, advancement in technology, the requirement also is increasing, or new requirements are popping up. So that also is catered by power electronic solutions, most of them through power electronic solutions only. Okay, so present day automobiles, you can see over 200 individual electrical loads. Can you imagine that? So that is why power electronics is deployed in a huge way in a electric vehicle. So some examples are listed here. Headlamps needs some level of voltage, some magnitude of voltage, DC voltage. Tail lamps, then cabin lamps, starter. Starter is a motor, right? So that in a ordinary IC engine or a hybrid engine, you are having a starter motor also. Yeah, of course, in a purely EV electric vehicle, you don't have a starter motor. Yeah, then fuel lamp, wiper motor needs power, blower fan. So just I don't want to list or read all the individual loads. Still, I just want to tell you like this, if you list, you can see around 200 individual electrical loads inside an electric vehicle, modern electric vehicle. And the power requirement is more than 8,800 watts for these loads. This is other than the drive motor, power required for the drive motor. Okay. So the challenging electrical and environmental conditions in the modern automobile have a strong impact on the design of automotive power electronic equipment. Okay. So this is one thing. When you design a power electronic solution for an automobile, that is totally different from a power electronic solution for a household appliances. Because in household appliances, you don't have this environmental challenges and mechanical issues. Like the vehicle is continuously undergoing vibration. Vibration in all the 3 dimensions will be experienced by even the power electronic part of the electric vehicle. So you see, there is every chance that some components can come out from the mounted position, which will destroy the system. So that is one important challenge faced by an electrical engineer. Another thing is environmental. For example, the car, when it goes through a highway, suddenly the rain comes. So due to rain, the water is trying to rush into the equipment, right? So that water is not pure water. It's having all type of contamination, including the various types of salts, acids. Everything is available or made. Everything is there in that muddy water. So that is again causing corrosion. That is causing issues to the power electronic systems. And also the temperature. Say now the car is going through a highway where the temperature is normal in Indian conditions, it is around 30-35 degree. But when you go take the same car to European countries, you may experience the temperature as low as minus 20 degrees centigrade. So even at that temperature, my power electronic device should work. Same way, the same vehicle running in a desert will have to tolerate more than 60-65 degrees centigrade temperature. The atmospheric temperature itself will be more than 55 degrees centigrade in the deserts. So that's what is the environmental challenge that has to be addressed by the power electronic designer for a vehicle, electric vehicle. Okay. And the electromagnetic interference. The power electronic solution you are giving should be susceptible to electromagnetic interference. That is one major thing. When you travel through a road, you don't know the kind of electromagnetic interference that will be faced by your power electronic system. If you are going through a road near a big factory for arc furnace, for example, lot of electromagnetic waves are emerged from the arc furnace. Heavy current is switched at high frequency. Definitely, you will be experiencing heavy electromagnetic interference. So the power electronic component you are designing should be susceptible to this electromagnetic interference. So that is another challenge a power electronic designer, engineer has to face when it comes to electric vehicle. So more than 95% of the electric power is processed before it is utilized. So this is what I have told you today. Whatever load you take, whether it is a fan, even an ordinary induction motor fan, when regulated through a solid state regulator, that is a power electronic solution. The solid state regulator, speed regulator, fan motor regulator is purely a power electronic solution. Conventionally, we were having resistance-based speed regulation, which was using much more power, dissipating much more power, wasting much more power. So the size also was very bulky. Those who have already used the conventional speed regulator, motor regulator may remember the size of that will be as high as some 15 centimeter to 10 centimeter to 5 centimeter. That much volume you should have for that regulator. Now, what is the size? Say some 2 centimeter to 1 centimeter to 1 centimeter. That is the size today. So you see, the amount of reduction you have obtained in the space and the efficiency. Efficiency of the conventional regulator was as low as some 40 to 50%, whereas now it is more than 90% for a power electronic based regulator. Okay, so that is why the first sentence is valid. More than 95% of the power is processed before it is used. As I have already told you, whether it is a fluorescent lamp, you are having LED, or the refrigerator, you don't have an on-off control now. It is all smooth control, the inverter control, or you are having an inverter AC or a smart TV. Everywhere it is processed, power is processed before it is used. Okay. So today's world of cutthroat competition, system availability and reliability plays a major role. So now we have seen why power electronics is important, how it is impacting our day-to-day life, and why power electronic engineers should be very happy about the electric vehicle and the new technology loads which we are using in our home or even the industry. Yeah, Now, the thing is, the power electronics is emerged, or it has emerged into a very, very big area. So even inside the power electronics, we are having specialization now. Say power electronics for electric vehicles alone. Don't discuss me anything, but the power electronics associated with only electric vehicles, or the power electronics associated with only the renewable energy. Say I'm having solar power, I'm having wind power, I'm having biomass based power generation. So you see, all these are possible just because you are having power electronics. Can you think about a windmill without power electronics? No. Can you think about a solar panel or solar energy tapping system without power electronics? Absolutely no. So all these emerging technologies are largely depending upon power electronics, and the availability and reliability is very important then, right? So availability of the power electronic equipment, reliability of the power electronic equipment, they are very, very important. That is why we are talking about today's topic, the condition monitoring, which ensures availability and reliability. So today it is the cutthroat competition. Whoever can sell the product at minimum cost, they will succeed in the market. Okay. So the quality and cost are two major things which decides your success in the business world. So that is one thing. So how can we improve the reliability of the power electronic system? See, failure is unavoidable, but we should have some way out of such failures. That is what is a condition monitoring. The best method is to have the condition monitoring. Yeah. So what do you mean by condition monitoring? Yeah, as the name indicates, continuously you assess the status of the device you are looking at or working with, whether it is power electronics or electromechanical or electromagnetic or electro-optical, whatever may be the load, you assess the health of that load, right? Once you assess the health of that load, you can assess how many more hours this particular gadget can survive, right? So then, if it is about to fail, better you replace that component with a better component, reliable quality component, so that the failure can be avoided. So to identify a failure before it is occurring, and suggesting a solution to overcome that is called the condition monitoring. That is the topic. Okay. So the reason is what I have told you. Power electronics is very having a very huge impact in our day-to-day life. Everywhere we are having power electronics, and hence the total system reliability depends upon the reliability of the individual power electronic solutions. So that is why the reliability becomes an important topic. That is why we are discussing this condition monitoring today. So the major concern in this aforementioned system is the reliability, which is responsibility for economic or safety considerations. So everywhere, economic, I have told you, when you met with a breakdown in your factory, you will be losing the production. So instead of manufacturing 10 cars, I could manufacture only 9 cars because there was a disruption in the operation. Maybe the motor was failed, or maybe the power was failed, maybe the power electronic part was the failed, whatever may be the reason. Till the time it was it is getting repaired, the total system will hang. The manpower will be wasted, material will be wasted, raw material will be wasted, everything will be wasted because you are having a breakdown in between. So that is why I have told you the reliability and availability is very, very important today. Say that case of a electric vehicle, say at 9 o'clock you are having a flight. You started at 8 o'clock from your home in your vehicle. Suddenly, it breaks down. Okay. So then what will happen? You will not reach the place in time. You will not reach the railway station in time. You will not reach the airport in time. You will miss the connection flight. You will miss the connection train. So your entire travel will be wasted. You may you may not be able to attend a meeting, right? You may not be able to write an exam because the flight was missed or train was missed, just because you are having a failure in your electric vehicle. So once you start from your home, you cannot afford to stop in between, unless otherwise it is warranted. Okay, so automatic or unexpected breakdown causes a lot for us. Okay, so if you miss a bus or miss a flight, when will you get the next flight ticket? Tomorrow, day after tomorrow, it may not be available. So you will not be reaching the destination in time, which is a huge loss for you. So you are having a client waiting in the other end, maybe at Delhi, but you couldn't reach Delhi because you missed the flight. Okay, so that flight was missed just because you had a breakdown in your vehicle. Okay, so that way the availability and reliability is very, very important. And that is where the condition monitoring is very, very important. So yeah, even in the photovoltaic cell, for example, if your photovoltaic cell is delivering power to you, suddenly the power delivery was stopped. What will happen? Maybe it may last for some more few more hours. After that, the total solution will be lost. You will lose your power. Okay, so the production have to be stopped. The manpower will be wasted. All these issues will pop up. So that will ultimately increase the cost of your product, because whatever loss you have incurred has to get back from the good products. Okay, yeah. So definitely the cost of such good products will go high. So you will not be in a position to compete in the market and you will be out from the market. So that is what I have told you. It costs a lot in terms of money, in terms of your reputation, in terms of your market, everywhere. So you can't afford any failure as of now. In today's world of cutthroat competition, you cannot expect a unexpected, you cannot tolerate an unexpected failure. So that is why condition monitoring is important. Yeah, so the mainstream efforts for improving the reliability and availability are standard-based reliability assessment. Basically, that will come up only in beginning when you are having a design. Say, I want to design my motor drive. Okay, there the standard-based reliability assessment can be done. Second one is fault tolerant topology with redundant components. That is another possibility. So what you will do, say I am having a motor in my vehicle which was driven by a inverter. Later on, what I will do, I will add one more inverter to drive the motor. So what will happen for that motor? If there is a failure in the converter, for example, an inverter is supplying the motor. So if there is a failure in the inverter circuit, what you will do? Yeah, total vehicle will be stalled. You cannot do anything. You cannot go ahead. You cannot go backward also. So what you will do? Instead of the faulty inverter, fix another inverter and continue your operation. Battery is intact. The motor is intact. Everything is intact. Only the converter part is failed. So you keep another converter. What will happen? Whenever one converter fails, the other converter will take up. It's a hot swapping arrangement. Maybe you have to do it manually. One DP switch have to be used to switch between the two controllers, right? So when the controller fails, you switch on to another controller, isolating the existing controller. So that is called redundant based fault tolerant operation. So how it will solve the situation? What is the disadvantage of the such a topology? Redundant one. I am using one more inverter. I am using one more motor. Whenever the first motor fails, use the second motor. Okay. Yeah. Whenever the first converter fails, use the second converter. Like that, a redundant unit or a spare unit is kept. So whenever you are having a failure, make use of the redundant unit. So that is called fault tolerant topology with redundant components. Now, can you tell me, can anybody tell me what is wrong with such a topology? Anybody?
It's costly, sir.
Yeah, very good. One reason is if you keep two inverters instead of one inverter, you have to pay more money because two sets of components, power components and control components are available. So definitely it is costly. Very good. Anything else? Other than costly, what can be another major reason of concern for an engineer?
One reason is mentioned in that chat box, sir.
Yeah.
Unused components, size increases, etc.
Size increases. Yeah, good. Yeah. So size is another reason. Say, instead of one inverter, I am keeping two inverters. So I need more space in the vehicle, which will be used by my components, not by the passengers. So the size is another very big concern as far as an engineer is concerned, right? Considered. So whether it is a launch vehicle or an electric vehicle or your laptop or your mobile phone, you want the size to be as small as possible, compact. So this will become an issue. If I want to use one inverter, I will keep one more inverter as a standby, one more motor as a standby, everything redundant. So even if it adds to the reliability, cost and size are major concerns for that particular method of for improving the reliability and availability. Third one is prognostics and condition monitoring, right? So that is the most promising one I want to discuss in length. So what we will do, we will monitor it and identify that there is a fault which is about to happen well before the fault occurs. So that is called the prognostics. Okay. Yeah. So that is a very important reliability improving method, which is widely used nowadays. And then designing highly reliable power electronic devices using advanced materials. For example, in the power electronic switch, MOSFET switch, what is the latest trend nowadays? In the switches, MOSFETs or IGBT, with reference to the material, what is the advancement? You are having WBG materials, right? Wide band gap materials. Instead of silicon, you are having silicon carbide. Okay, so silicon carbide kind of materials are called wide band gap materials. So that material gives a better equipment in terms of reliability and the parameters. The MOSFET using or IGBT using silicon carbide can be operated switched at much higher frequency than a IGBT manufactured using silicon. Similarly, a WBG switch can be operated at a higher temperature than a silicon switch. So, in a nutshell, I can tell if you improve material quality or the there are a lot of improvements in the materials also today, material management, or I mean the nanoscience has come up. So a lot of new components are coming up, new materials are coming up in various areas. Okay, so as polymers, fibers, so many different materials are invented and that are used for various applications. You see, nowadays, nailless paste is available or adhesives are available. You don't need a nail to affix one piece of wood to another piece of wood. Better quality adhesives are available. That is a outcome of the material engineering. Okay, so a lot of advancements are taking place in materials. So use better materials and improve the reliability. So that is yet another method of improving the reliability and availability of the electrical system as a whole. In electrical or power electronic system, as I have told you, use any WBG materials, wide band gap materials, based switches to improve the reliability. Yeah, and then in the case of the standard-based reliability assessment, I have told you that will be used at the initial stage, design stage. After that, that don't have much of an importance. What is it? The components will be having some standards met. For example, I am buying my AC. The AC, I am ensuring that it is having 3-star rating or 5-star rating. Higher the number of stars, better is the power efficiency. So if you want to improve the power efficiency, you should use better components. You should have a better design. So overall, the reliability will improve. So that way, that kind of ISI mark. So I purchase a component with ISI mark only, right? Say pipe I am buying for my plumbing, or the wire I am buying for my wiring. I'll ensure that I'll be using only ISI marked one. What is that ISI mark? That is a standard, ensuring or guaranteeing minimum quality. Okay. Yeah. So that is called the standard-based reliability assessment, where MTBF is the main criteria. What is MTBF? Mean time between two failures. So that is a statistical data. Mean, yeah. So every component, say I am using IRF 640 MOSFETs or TMS 320 microcontroller, all of them will be having an MTBF, mean time between failures. That data usually will be given by the manufacturer. So manufacturer will be tracking his product out of the experience and the feedback he is having. He will be having this MTBF information that will be published in the website. Okay. Yeah. So you should use the component which is having higher MTBF. Higher the MTBF, better will be the component, definitely. Yeah. So say I am having 10,000 year life for my LED light, right? So such a data is made available by the manufacturer to the user. So that is what is called the standard based reliability assessment. And I'll be ensuring that I'll be using ISI marked one or say 5-star marked one or the one with having much more MTBF, etc. Okay. Yeah. So that is how you ensure the reliability. Now, although the fault-tolerant topologies with the redundant components and power electronic devices is advanced improved reliability, that do not prevent failure from happening, right? So that is one point you should note. Whatever care you take, failure is definitely not 100% avoidable. Some failure at some point will happen. Okay, so failure is never completely preventable. That is a point. So the preferred way is to take action before the failure occurs. Monitor the condition and initiate the action before the failure occurs. That is the best way, right? Because failure is never 100% avoidable. So if used in the design, lifetime prediction model enables designer to make use of the data and predict what is the RUL. What is RUL? Remaining useful life. Right? So now I have used my car for 5 years. In the next 1 year, whether there is any chance for any of the components to fail, right? Or whether I can use my car for 1 more year without any failure. That concept is called remaining useful life. Say I am having a refrigerator which was already 10 years old. So at any time, it can fail. So what I can do? I can assess the operation and identify how many more years it can withstand. So that is called the remaining useful life calculation. Okay. Yeah. So if you clearly exactly identify the RUL, what is the advantage? We can schedule a maintenance. We can schedule a repair. Need not wait for the breakdown to occur and take a corrective action, repair action. Right? So that is the beauty of the condition monitoring, through which the RUL can very well be predicted. Without condition monitoring also, manufacturers will be giving the MTBF minus the used hours will give you the remaining useful life. So that calculation is again a nice way of handling the issue to improve the reliability and availability. Okay. Yeah. So previous studies show that a majority of power electronic systems failure are due to component failures. So then you concentrate on the component failures so that the total system quality or reliability can be improved. Okay. Yeah. Now, how to find out the remaining useful life? For that, you need experts from many areas of engineering. Electrical engineer, for example. Say I am having a MOSFET used in my car. How many more hours I can use that MOSFET in that car? For that, an electrical engineer's role is to tell whether it has undergone any abuse. Say my MOSFET is 600-volt MOSFET, but I prefer to operate it at 500-volt or even less than 500. Because at 600-volt, every chance is there that the total system will fail. Okay? Yeah. So what I will do, I will not use at full maximum ratings of the device. Similarly, current. Say I am having a 10 ampere MOSFET, 10 ampere IGBT. Does it mean that the maximum current that can be carried by the MOSFET is only 10 ampere? No. Instantaneously or for a small duration, much more current can be carried by the same MOSFET. Right? Yeah. So I should know whether any such conditions had occurred in the history of operation of the device. So that is the role of electrical engineer. By any means, electrical engineer will identify the issues and he or she can tell, say, this many times over voltage has occurred, 5 times under voltage has occurred, 2 times over current relay was tripped. Understood? So they are all conventional methods to overcome the abnormality. Fuse, for example, whenever the current increases beyond a limit, the fuse will blow and the equipment will be protected or the path will be protected. Okay? Yeah. So what I would like to tell you is such abuses will definitely degrade the components. Instead of 10 ampere, I pass 11 ampere for 7 microsecond. Device will not fail, but it will be degraded. Its life will be decreased. Okay? Its performance will be inferior. So like that, the total degradation can happen if you abuse the devices. If it is a switch, over current, over voltage, etc., which can very easily happen. If there is a lightning, over voltage can happen. If there is a short circuit, over current can happen. So such phenomena are very common, but it will not be failing the device instantly. It can tolerate the MOSFET can tolerate that higher amount of current and voltage, but issue is it will be degraded and a number of degradation will finally result in the failure, no doubt. Okay. Yeah. So that is the electrical engineer's part to tell that this much abuse has occurred. Say this much increased voltage was applied, this much increased current was flowing. So due to which the life will be less. Then mechanical engineer. So that person is the engineer behind removing the heat energy from the junction of the semiconductor. Am I right? Yeah. So heat energy will be generated in the junction of the semiconductor, which will be dissipated to the surroundings using heat sinks. Natural cooling also is there. If the temperature is not that high, better you don't use any heat management. Automatically, the temperature will come down after some time. Okay. Yeah. So that is because the generated energy is getting dissipated to the surrounding air. So the temperature of the IC or the PCB should never be more than the temperature of the surroundings, isn't it? So when the temperature is more, the heat energy from the board, PCB or whatever it may be, will be dissipated to the surrounding area. Yeah, mechanism is different. One may use a natural cooling without anything, automatically it cools. Another one may use a heat sink, simple heat sink without any cooling method, just a heat sink attached to the semiconductor. So whenever heat is generated, that heat will be carried by the heat sink to the surrounding area. Or you use a fan to cool down the heat sink. Okay, so direct a fan towards the heat sink so that the forced air will get continuously circulated and hence the temperature comes down. Okay, yeah. So that is another reason why mechanical engineer is required in this scenario. So if the heat is removed, then the chance for failure will be less. Okay. So the mechanical engineer should tell, if you turn on like this, turn off like this much voltage, this much current, this much heat will be generated. And if you use this particular heat sink with this particular blade or the motor, the method is called forced air cooling. Using a fan, you forcing the air towards the hot body so that it gets cooled down. Right? So that is called forced air cooling. Another one possibility is to circulate some fluids around the heat sink or inner part of the heat sink carries some fluid. That fluid will absorb the heat energy than the surrounding air. Okay. Yeah. So that is guided by a mechanical engineer. So that is why I have told you the reliability assessment mechanical engineer is important. And the statistician, definitely, the mean time between failure. What is that mean? Yeah, mean, median, mode, everything is actually statistical methods to analyze the data and reach in a conclusion. So the better tool you are having, you will get more accurate predictions. That is why statisticians are important in the lifetime prediction. Ultimately, we need to know what is the remaining useful life. Okay. We need to understand the dominant failure mechanisms in order to predict the lifetime of the power electronic devices. So we have seen what is the importance of power electronics. Next, we have seen what is the importance of reliability and availability. And then the third one we have discussed about how to incorporate the reliability or availability. Okay. Yeah. Or how to improve the reliability and availability. And in the next one, we will see the failures of mechanism. Unless otherwise you know the failure of mechanism, you cannot predict the mechanism. Okay. Yeah. So that is what we are going to discuss in the next slide. So before that, any doubts you are having till what we have discussed in the class? Any doubts? Anybody? No doubts. Nobody is having doubt. That is not a good sign. If you have any doubts, you can stop me and ask me. No doubts as of now.
No, sir.
Yeah. Okay. Then I think we will break for 5 to 10 minutes and then continue our session. Okay.
Okay, sir.
Yeah, welcome back to the session. So we will identify what are the reasons for the failure. So I have told you it experiences thermal, chemical, electrical, mechanical stresses, due to which it degrades gradually, leading to complete failure. Now, in electric vehicles like situation, hybrid electric vehicles, the IC engine will be emitting lot of heat energy, due to which the temperature of the surrounding area will be high. So the power electronic equipment has to work at a higher temperature than the ordinary. So that is another challenge in the hybrid electric vehicles, which will not be there in pure electric vehicles, definitely. Yeah, so there are two reasons for the failure. One is chip related or intrinsic failure, package related or extrinsic failure. So intrinsic failure is electrical overstress. High current and high voltage are the reasons for electric overstress. And the thermomechanical are the reasons for extrinsic failures. Another major failure reason is the difference in the CTE, coefficient of thermal expansion. What is CTE? That is, say, if I increase the temperature by 1 degree, how much will be the increase in the physical dimensions? That is called CTE, coefficient of thermal expansion. So that will be different for different materials. So CTE difference is another reason for the mechanical stress and ultimate failure. Yeah, latch up is another reason for the failure. For example, in the case of a SCR, silicon controlled rectifier, there is a cross section looks like PNPN. 4 layers are there, semiconductor layers are there. And hence, 3 junctions will also be available. So that is how the silicon controlled rectifier is working. And that is having a latching current. What is it? When the anode current is more than the latching current, it will continue to conduct even if the gate is not supplied. Right? So usually the SCR will be turned on by applying a gate voltage. So even if you remove the gate voltage, when the current is more than the latching current, the anode current is more than the latching current, the device will not turn off. It will continue to conduct. In other words, the gate will lose the control when the latching current is exceeded. Right? So that is one of the triggering methods in the SCR. Currently, if you see a IGBT or MOSFET, there is an inner cross section where you are having this PNPN type of layers. So if there is a possibility to latch up, what will happen? The gate of the MOSFET or the gate of the IGBT will lose the control. So how are we turning off the MOSFET? By removing the supply voltage, gate voltage. You can turn off the MOSFET. Now, if a latching up occurs, even if you remove the gate voltage, gate supply, the IGBT will not be turned off. It will continue to conduct. What will be the side effect? A switch which is supposed to be turned off is still conducting. Same time, another switch by nature will be turned on. Both these on switches will create a short circuit across the supply, dead short circuit across the supply. As a result of which, the entire path experienced huge current, short circuit current, which spoils the show. Even the PCB will be burned, even a fire may break out. You must have read the news recently. A charging two-wheeler was exploded. That they identified as a battery issue, right? Yeah. So that is what is the result of a latching up kind of situation. So try to avoid latching up to the extent possible. So one of the reasons for latching up is high dV by dt. What is dV by dt? Rate of change of voltage. So whenever you turn off the device, the voltage across the device will be increasing from 0 to the blocking voltage, 230 or 640 or whatever it may be, right? So how much time it will take to block a conducting device to block? It will take only nanoseconds or microseconds time. So if there is a change from 0 volt to 1000 volt or 100 volt in 1 nanosecond, what will be the dV by dt? 10 to the power of 11, right? Or 0.1 into 10 to the power of 10. I mean 10 to the power of 12. So such a huge dV by dt across a small capacitor itself. What is C into dV by dt? C into dV by dt is I, current through the capacitance. So any semiconductor device, when it is turned on, looks like a capacitor. As two sides of that is having conducting plane, and in between you are having the insulating plane, right? So that is as good as a capacitance. So a capacitance C with a huge dV by dt can conduct a huge current, say 1 microfarad current across the 1 microfarad capacitance. Across that capacitance, I change from 0 to 100 volt in 1 nanosecond. Then what will be the current? 1 microfarad into 10 to the power of 11. How much? It will be more than 1000 ampere current. A 1000 ampere current through a capacitance is much sufficient either to latch it up or to destroy. So avoid high dV by dt. That is another way in which you can look up the latch up current. Right? So the another failure mechanism is the latch up current. High temperature also can induce latching up. The current will be high enough to latch up the NP-NP path at high temperature. Yeah, electron migration is or metal migration caused by high current density at high temperature is another reason for failure. As a result of electron migration, voids will be created between metal and what is void? It's an air cup. So air will not be conducting heat very fast. It's not a good conductor for heat energy. So if you are having a void, less heat energy only will be dissipated to the surroundings, due to which the device temperature can be increased, right? So increased resistance for the thermal resistance will be more, and hence the temperature, junction temperature will be more, as a result of which a device failure can occur. So electron migration is another reason for the device failure. And this is what is called the cross-section of a semiconductor switch or a semiconducting device. You are having a base plate over which you are having a solder to connect the copper with the base plate, then a ceramic to separate these two copper things, and then a solder to connect the chip to the lead, connecting lead. Okay, and a bonding wire must be a high conductivity wire. Some people are using gold also to improve the performance as the bond wire. Yeah. So you see how many materials are there? Base plate is made out of one material. Solder is made out of tin and lead, copper, ceramic, it's an insulator even. Then again, solder material, chip, silicon material or silicon carbide material. So many different materials are available. Each of these materials are having different coefficient of temperature expansion or thermal expansion, CT. So what will happen? Say, now the temperature increased from 20 degree to 50 degree. What will happen? Temperature of this copper will increase. This chip will also increase from 20 to 50 degrees centigrade. Due to the difference in CTE, the height of this copper is increased from 1 mm to 1.01 mm, whereas the height of the chip is increased from 1.5 mm to 1.55 mm. So you can see there is a difference between these two planes, top of the chip and the top of this copper. So if there is a difference in the distance, what will happen? This connecting wire will experience a strain. Am I right? So yeah, there is a fixed distance between this surface and this surface, which were connected using a constant length bond wire. Now the temperature changes. As the temperature changes, the difference is there in the expansion of this material and expansion of this material. As there is a difference between the expansions, there will be a stress experienced by this bonding wire. As the stress is there, what will happen? Yeah. That stress prevails, and there is a chance that this joint can come out or this joint can come out. Am I right? That may not be very strong edge bond. So if there is any weak point is there, that will come out as there is a huge stress due to this cross section. Understood? And now the temperature came down to 10 degrees centigrade. So from 20 it went to 50 degree. From 50 again it came back to 20 degree or 10 degree. Okay. So what will happen? Again, the shrinking of this will be better than shrinking of this. Again, there will be a difference between the distance between this surface and this surface because the expansions are different. So whenever there is a difference between these 2 points, distance between these 2 points, this bond wire will experience a stress or a compressive force. So when the number of cycles are more, say 50 times, this is happening in 1 hour. Temperature increase from 20 degree to 50 degree. After some time, it went back to 10 degree. Again, it went to 20 degree, from 20 to 50 degree. Such a cycle, if it is repeated, what will happen? Definitely, this bond wire also experience a cycle of stress and strain. These joints are also experiencing continuous cycles of stress and strain. This will weaken up and ultimately break down. Am I right? So this is the problem that can happen due to difference in coefficient of thermal expansion, CTE. Okay. So bond wire failure can occur, or solder fatigue can occur. These solder points can be fatigued, and aluminum reconstruction also can occur due to the cyclic change in the temperature. Right? So that is an extrinsic reason for failure. That will ultimately fail the total IGBT or MOSFET or whatever solid state device you are using. Yeah, another one, the void increases the thermal impedance. Say if there is a void created, gap between two conducting surfaces, then what will happen? That area will not be available for conduction. So the remaining area will experience more density of conduction. Maybe it is temperature, maybe it is current. So current density will increase, or the temperature density will increase. Okay. So what will happen? The temperature will increase. When the temperature increases, again void increases. Right? So when the void increases, again the conduction density increases, temperature increases. So that is why we are telling it as a positive feedback. Effect causes more void causes more temperature causes more void. So like that, it's a positive feedback mechanism, and that fails the total system. Right? So that is another failure mechanism possible. Aluminum reconstruction, same way, is another reason for the failure. Aging will happen or degradation will happen due to that. Yeah, so this table tells in detail how this failure occurs, what are the reasons for the failure, at which location the breaking occurs or failure occurs, and what are the modes of identification, what parameters are getting affected by that. For example, if latch up occurs, it occurs in the silicon die. Reasons are over voltage, irradiation, electric field, or over temperature. Okay. Yeah. So all these are reasons for latching up. And the device will burn out because heavy current will flow. Okay. And the loss of gate control, you can, even if you remove the gate voltage, it will not be turned off. So you can't loses the control. Okay. Yeah. So parameter affected is VCE on time collector emitter voltage. Yeah, lifetime prediction. There are two methods. One is empirical relation based failure prediction, or another one is physics of failure based failure prediction. Both are possible in the lifetime prediction or remaining useful life, RUL prediction. So what is the mechanism for failure? That you identify. We have already discussed many mechanisms. So by identifying that physical reason, you can avoid that. So that is called physics of failure based remaining useful life prediction. So I know it has already undergone, say, 50 degrees centigrade. It was operating for 1 hour at 50 degrees centigrade. So there will be a degradation, right? So reason for the degradation is increase in the temperature. Okay. Yeah. So how much degradation will happen? That study I have to make. And then I can predict if it was supposed to operate at 40 degree. It operated at 50 degree for 1 hour. So this much degradation has occurred. So this much more life it is having. There is a possible failure after 1 month. Otherwise, it must have happened after 1.5 months. Right? Yeah. So that is called the physics of failure based lifetime prediction. Empirical formula based also is available. You can form empirical formulas using parameters. As electrical engineers, we always wish to have electrical parameters, resistance, capacitance, inductance. Even in the model, we introduce these parameters, right? If you want to model the building, stress and strain experienced by a mechanical construction, what we will do? We will take the electrical analogy of the mechanical construction, mechanical structure, right? Yeah. So in terms of R, L, and C, we identify the parameters and then we will analyze it. Even the temperature, if I want to design a heat sink, that also I can define it as electrical parameters in terms of electrical parameters. Say, for example, T1 is the temperature of one body, T2 is the temperature of other body. T1 minus T2, right? The energy flow will be directly proportional to T1 minus T2. It is similar to V1 is the potential of one point, V2 is the potential of the other point, and the current is proportional to the difference between V1 and V2. Right? Yeah. So like that, we are actually converting every mechanism or every physical phenomenon into its electrical equivalent and then analyzing it. Okay. So, excuse me, that method is called empirical formula based or modeling based failure analysis or lifetime prediction method. So in the empirical analysis also, many standard methods are available. So NF is the number of cycles yet remaining. Temperature swing delta Tj and junction temperature Tm. In terms of these three parameters, they have derived an equation to identify the remaining useful life. Yeah, so NF is equal to A into delta Tj to the power of alpha exponent Q by RTM. Okay, so this is one of the empirical equations. There is no theory, physical or scientific theory behind this equation, but empirically from experience, we know that this relation is very good, hold good for the calculations. That is why it is called empirical relation. So here R is the gas constant, Tm is in Kelvin, A is equal to 640, alpha minus 5, Q is 7.8 into 10 power 4 joules per mole. Right? So it is based on Coffin-Manson Arrhenius model. Right? So this Coffin-Manson Arrhenius model considers only very few parameters. And we engineers know these are not the only parameters which affects the life. Then what? Yeah, the amount of current flowing in that circuit. And then duty ratio of the switch. Then peak voltage and peak current of handled by the switch. Frequency at which the switch is operating. All these will affect the lifetime that we engineers know, electrical engineers know. But those parameters were not appearing in this empirical equation. So what we can do? We can improve the accuracy of this calculation by adding such logical, scientific non-parameters. Okay, so this is how I have modified it. K delta Tj to the power beta 1 exponent of beta 2 by low temperature into T on to the power of beta 3 or into beta 3 also. I current to the power of beta 4, voltage to the power of beta 5, and duty ratio to the power of beta 6. You see, I have considered all these electrical parameters into the empirical relation. What will happen? I am sure that this prediction will be much better in the near future because we have considered much more parameters into account. And what is the challenge here? To identify beta 1, beta 2 up to beta 6. That is not an easy task. You have to do a lot of statistical work, a lot of samples you have to take. Only after doing all these things, you can reach into such a expression. Okay, yeah. So many such empirical equations are available using which you can identify the lifetime. Yeah, these are some more examples I have provided for you to Google and get the details. Norris Landsberg model, that is this expression. And one more model I have provided here, which is having a frequency term also. Yeah, so many such analysis were done. So if you want to do research, definitely you can play around with such empirical relations. There will be always a room to improve the empirical relations. Get better accuracy, better results. So number of cycles before failure versus the crack length. Such a plot also is provided by some of the authors. So we are having the lifetime prediction models using such empirical equations. So what we can do, we can predict the remaining useful life. Say I know that my vehicle is having a inverter. That inverter will fail in next 5 days. So what I can do? If I know that well in advance, I can arrange a repair or a replacement. Okay? Yeah, so that is one possible method to avoid failure. So that is by using real-time life estimation. On the go, continuously, you monitor the device. For example, if I am using an electric vehicle and a motor is used, how can I monitor the motor? By monitoring the voltage and current, I can monitor the motor, right? Say whenever there is a difference in the current or voltage, I can identify something is wrong, right? Yeah, how the doctor is identifying the heart attack? By monitoring the ECG. Same way, for the equipments also, we should identify some methods using which you can predict the health condition, right? So that is called the real-time life estimation, real-time condition monitoring. Okay, so as far as a motor is concerned, if I tell you, easiest one is to analyze the current, motor current. Okay, anyway, we will see it. The Miner's rule is there. Yeah, so using Miner's rule, you can predict the system lifetime if you know the lifetime of individual components, right? Say, my inverter is having 10 hour or 10 days lifetime. Its total lifetime is 20 hour. My motor is having 15 hour. Its total is some 30 hour. Like that, if you know the individual components remaining useful life and the total life, you can predict the total life of the system formed by integrating these devices. So that is called the Miner's rule, where the linearity is assumed. That is a challenge definitely, but they assume the linearity, and definitely it is a good approximation. Absolutely no much difference, damage in the calculation accuracy, even if you are having this linearity assumption. Another most widely used method for the remaining useful life calculation is rainflow counting algorithm. For example, my vehicle is running between 2 points, a source and a destination, every day. So the vehicle will be undergoing a particular profile every day. Say there will be a climbing hill. There is a hill. So the vehicle will be climbing that hill for some time at a particular slope. After some time, a plain surface will be there for a long time, plain surface. After that, a ramp down also is there. Ramping down also is there. So when you want to climb the hill, ramp up, climb the ramp, the motor will be experiencing more current, more power, more torque. All the associated electric accessories also will be experiencing all these, more current, more voltage, more power, etc. Then the one which is experienced when the vehicle is running in the flat surface. Similarly, when you come down, ramp down, the energy is excess. mechanical energy will be excess. Don't use any electrical energy. Instead, it can generate electrical energy, regenerative braking. Then the stress associated with the electrical components are totally different. Understood? So this is called the road profile. How many climbings are there? What will be the length of each climbing, height of each climbing, for how long it will experience that climbing. So road profiles are published. Nationwide, it is published. If you Google it, you can see road profile. So using the road profiles only, the design engineer can decide whether this particular component will work for me in my electric vehicle if it is running in this terrain. For India, you are having a road profile. In European countries, you are having yet another road profile. For US, Canada, everywhere you are having different road profiles depending upon the nature of the road, height of the road, width of the road, everything, right? So depending upon the road profile, you can calculate how many times my MOSFET will be turned on and turned off if my vehicle is running in that profile. Okay. Yeah, maybe you will feel it as a tale, fairy tale, but no, it's a scientific fact. Robert Bosch, I know, is using rainflow counting to understand the remaining useful life of the MOSFET used in their inverter in the electric vehicle. Okay, so I had a work on that. They were really appreciating the modeling we have developed, and they could get a very good accuracy in the calculation of remaining useful life using the rainflow counting methods. Yeah, another beautiful and very encouraging or demanding area is precursors. Precursor-based lifetime prediction. What is that? Precursors are nothing but forerunners or indicator of the event. Right? Suppose I am traveling in a train. When the train slows down, what will be your inference? Yeah, a train is approaching a station, or the train is about to stop in a station, right? Or in a signal. Train didn't get signal, so it is about to stop. So due to both these reasons, the speed of the train can come down. But when you observe many people walking towards the door of the compartment, definitely you can very well predict that, yeah, an important station is about to come and train will stop in that important station. Right? So that can be used as a precursor for reaching into that conclusion. What is that? People walking towards, many people walking towards the door of the compartment, plus the speed of the train coming down. Okay, not the Bombay suburban train, definitely. The normal trains running in Kerala only I am talking about. So anyway, those who have experienced the Bombay suburban train will definitely appreciate what I am telling. It's really an experience. Those who didn't do that should experience it. The challenge you are facing in entering into a train and getting out from the train is beyond explanation. Okay, one should experience and understand what it is. Okay, anyway, so here the precursors, such indications can be analyzed and monitored. First, what you should do? Analyze the phenomenon and identify a precursor. Once you identify the precursor, you can monitor it continuously and predict the events. Okay. So how to, another technical term for precursor is feature. Fault detection feature, F-E-A-T-U-R, feature. So precursors or features have to be first identified. Identifying a proper feature or a precursor is a challenge for the engineer. Lot of works are even now happening in this area. Very challenging task. Still, lot of works are possible in the precursor identification and precursor monitoring. Can you tell me what can be a precursor for a MOSFET or IGBT? This can indicate an imminent failure. So if the precursor changes, you can tell that there is a failure about to occur. So how can you identify the precursor? One method that can be used is the accelerated aging. Say, I am having a MOSFET used in my solution. Can I wait for 15 years to identify the precursor or predict? This can be a possible method of identifying the failure? No, absolutely it is not possible. I can't wait for that much long time. Before that, all the things that should happen could have already happened. So what I can do? I can do accelerated aging tests. I accelerate the aging of the device. How? By abusing it. Controlled abusing. Okay. Suppose my MOSFET is capable of taking 10 ampere current. What I will do? I will keep this MOSFET in a chamber, environmental chamber. Increase the temperature of the MOSFET to 150 degrees centigrade. And then pass 11 ampere current for 1 second. What will happen? Normally it will be working at 50 degree. Now I take the temperature to 150 degree. 150 degree. Normally it has to take only 10 ampere current. I force 11 ampere current. So what is that? Abusing it knowingly in a controlled manner. What will happen on that abusing? Its performance will degrade. The degradation will happen. Okay. So if you were using this MOSFET at 50 degrees centigrade and 10 ampere current, the same degradation could have been occurred only after 10 years. That I am achieving by setting the temperature to 150 degrees centigrade and passing 11 ampere current for 1 second or 1 hour. Understand? So instead of waiting for 15 years, I am accelerating the aging process. Same degradation is achieved in 1 hour time. Understood? So that is called accelerated aging method. So once I age it to 15 years, what I can do? I can analyze all the parameters. Which are the parameters changed drastically? And then that can be declared as a precursor, which I can monitor continuously. So at the end of the lifetime, that parameter will be showing a change, indicating a failure, possible failure in due course. So what I can do, I will send it through my communication channel to a cloud. This cloud belongs to the manufacturer of the vehicle or any machine. OEM, original equipment manufacturers, cloud. My IoT device will be continuously posting this data. So the cloud on analysis understands that this particular parameter is showing a variation now, due to which the software can predict that a possible failure can happen. Understand? So this is how the real-time monitoring is happening. Understood? Instead of cloud, my IoT can also send a message, SMS, to nearby workshop or service center, from where the experts can come and attend the issue. That also is a possibility. Yes, I have told you, vehicle today, I want 100% availability. I can't afford a single failure of my machine, my vehicle. It will cost a lot to me. I can't reach in time. I will lose my business. My priority will be lost. I will lose my reliability. Nobody will believe me if I am continuously late. Punctuality is a quality, right? I will lose that. So I can't afford even a single breakdown in my vehicle. So what I can do? Identify a precursor. Monitor it continuously, either in the ground level, in the vehicle itself, or in the cloud. And then the cloud is made accessible to the technician. Right? Either way, the technician will get a message that this motor is about to fail. Motor in my vehicle is about to fail. So, end of the day, evening 6 o'clock, I reached home. At 7 o'clock, the person from the technician from the workshop comes with a new motor and replace my old motor. So what will happen? Tomorrow morning, without any issue, I can use my vehicle. So like that, the failure is prevented. Understood what I am telling? So this is the challenge of the engineer of the day, the reliability and availability. Okay, and this is how you can incorporate it. So now my question is, if you take a MOSFET, for example, what can be a precursor? Any guess? A wild guess you can have? A parameter which changes when the device is about to fail is a precursor. So as far as a motor is concerned, what can be a precursor? A MOSFET is concerned, what can be a precursor is the question. Anybody? No answer. Yeah. So on-state resistance, RDS on, resistance between drain and source when it is on. What is ideal RDS on? When the device is on, switch is on, what is the ideal value for RDS? Can anybody tell? Hmm? 0. I don't want any resistance for my switch when it is on. Okay. When it is off, it should send. When it is off, it should have infinite resistance. When it is on, it will be zero resistance. I don't want any resistance to be offered by my switch. If the switch offers a resistance, then it will be a loss for me. V into I loss. So RDS on must be zero. So whenever a failure is about to occur, the on-time resistance is showing an increase. 10 to 17% increase in the on-time resistance. Okay. So if that increase is observed, you can predict that I am having a failure, about to fail. Now, another method is, another precursor possible is gate threshold voltage. What is gate threshold voltage? Say, if you want to turn on a MOSFET, you have to apply a voltage to gate to source voltage. If that voltage is more than, say, 5 voltage, then the device will turn on. That is what is guaranteed. If it is 4 volt, device may turn on, may not turn on. But 5 volt, it will turn on. So that voltage at which the manufacturer ensures that the device will turn on is called gate threshold voltage. Usually 5 volt is a standard typical gate threshold voltage for a MOSFET, power MOSFET. So what we will do, we used to apply 12 volts to doubly make sure that it will turn on. So it is observed that when the life is almost completed, device is about to fail, this threshold voltage is increased. Earlier, it was turning on at 5 volt. Now, only at 5.5 volt, it is turning on. So what is happening? There is an increase in the threshold voltage, gate threshold voltage. So this is one of the precursors. Then ringing characteristics. When you turn on, it will not be a 90-degree turn on, 90-degree graph. Instead, in the corner, you will be having ringing, increase and decrease, a sinusoidal shape. That is called ringing. So ringing characteristics you cannot avoid for any switch inherent because of its parameters, inherent parameters, stray parameters. So if you continuously monitor the ringing characteristics, if the device is about to fail, you can see there is a change in the ringing characteristics. Maybe the amplitude of the ringing voltage increases or the frequency of the ringing voltage decreases, something like that. So by monitoring these ringing characteristics also, you can predict the possible failure, end of life. Okay, so this ringing characteristics can be a precursor. Then same way, on time. What is on time? The time taken for the device to block the current after removing the control signal, or that is called turn off time, or time taken for increasing the current from 20% to 90% of its total current once you apply a control signal, turn on signal. That is called turn on time. So both turn on time and turn off time are fixed for a device. But when a failure occurs or the device life is about to end, you can observe a considerable change in the turn on time and turn off time. Okay. Yeah. So that also can be a precursor. So now I have told you various methods to identify the failure in one component. If you take a capacitance, what can be a precursor? Anybody? For a capacitor, what can be a precursor? No answer. Yeah. ESR, equivalent series resistor. We can continuously monitor the equivalent series resistance, and if there is a significant variation in the equivalent series resistance, you can tell that the capacitance is about to fail. Similarly, if you want to identify the failure of a inverter, solid state inverter. What is an inverter? The power electronic device which converts DC to AC is an inverter. So how can you identify the failure of a component in the inverter? By monitoring either the output voltage or the output current, you can predict a failure in the inverter. Understand? Say the shape of the voltage or the shape of the current will drastically change if one of the components in the inverter fails. Maybe the upper half of the output AC will not be available, will disappear when the MOSFET fails, or the lower half, negative part of the AC will be totally absent in the output voltage. So all these can be considered as a precursor for the failure analysis. So monitor the output voltage of the inverter, continuously check whether every part of the voltage is available. If there is a change, you can either send an SMS to the user or the technician who can repair it, or the OEM cloud. All these are happening using IoT. Development in that IoT system also can be a challenging research area, right? Okay. And then the technician can attend the problem in time so that an unexpected failure is totally avoided. So this type of condition monitoring is today really important, and lot of researches are happening, and you can also do a lot of researches in terms of the precursors you can do, in terms of IoT based communication you can do, and then ML. Where is ML coming in? Machine learning coming in. Yeah, SVM is a machine learning tool. Support vector machine is a machine learning tool used to classify between two cases by classifier. So what it can classify? You feed the precursor to the SVM model. SVM model will give the output. If the SVM model output is positive, you can very well conclude that the motor condition is fine, or the inverter condition is fine, or the MOSFET condition is fine, or capacitor is fine. If the SVM output is negative, immediately you should understand there is a failure. Okay. So SVM is a classification tool used to classify between healthy component and faulty component, or healthy system and faulty system. Yeah, whether it is a component, a group of components, or a cascaded components, whatever it may be, it can be considered as a system, right? So when you monitor the system, you should tell whether it's a healthy system or a faulty system. Right? So that prediction or classification between healthy and faulty systems can be done using a SVM algorithm, support vector machine algorithm, or any machine learning model you can use. Navy Bayes method is there. Then ANN based classifiers are available. All these are solutions for predicting or telling you, classifying between a healthy motor and a faulty motor. Okay, or a faulty system. In general, it's a system. Whatever system you want, you can apply this principle. Okay, so in a support vector machine, what is the algorithm? Maximize the margin and minimize the error. Right? Support vectors are nothing but the points that appear nearest to the classifying line or classifying plane. A plane or line is identified if the point is falling into one side of the plane, it is a healthy motor. If it falls into the other side of the plane, it's a faulty system. Right? So the role of the system model, you input the incoming precursor. The precursor will be applied to the model. Model will clearly tell it belongs to upside or it is over the plane or under the plane. If it is over the plane, that means it is a faulty system. If it is under the plane, yeah, classification plane, definitely. It is a healthy motor, like that. Okay, so first what you should do, identify the precursor or the fault identification feature. For that, you can do a lot of researches. Second one, once you identify the precursor, you should monitor the precursor. Continuously, you monitor the precursor. That also is a challenge. See, for example, RDS on. How to measure the drain to source resistance when the switch is on? It is not very easy to do that in a used inverter. Switch is under use. It is working, running. Inverter is working. At that time, can anybody go and measure between drain and source? No. It is not possible. So monitoring the precursor is a challenge. In that area also you can do enough research. Once you succeed in monitoring the precursor, what you can do? You train an SVM, support vector machine. What are the data you want? Precursor at different conditions. For example, if you are trying to identify the fault in a motor, induction motor, what you can do? You conduct test at various conditions. Say at no load condition, at 25% load condition, 50% load condition, 75% load condition, 100% load. All these conditions, you experiment, conduct experiment. Get the precursors for all these conditions. And then when it is faulty, intentionally you generate a fault in the induction motor. Induction motor faults can be short between phase to phase, short between phase to ground, short between turns of the same phase. All these can be faults. All these faults will be having different precursors also. So you can model the failure of the system. Empirical equations can be used for that. And then identify the precursor. Get the precursor at various loading conditions, various input conditions, various output conditions, temperature conditions. In all these conditions, you acquire the precursor. Feed these precursors to a SVM algorithm. What SVM algorithm will do? Using optimization methods, it will identify a model based on your precursors you have fed. That phase of model development is called training phase. So in the training phase, you give the information to the model that this precursor belongs to a healthy motor, this precursor belongs to a faulty motor, like that. That information also you are supposed to provide to the system. Now, from this identified precursor, by running the training algorithm, a model will be obtained. Okay. There are two matrices obtained as the output of the training. A weight matrix and a B matrix. So these two matrices are the outcome from training of the support vector machine. Now, using these matrices, you multiply the newly incoming precursors. Understood? Now you are real-time monitoring the system. From the system, you derive the precursors. This current precursor, real-time precursor, you feed to the developed model. What will happen? The SVM will immediately come out with a positive number or a negative number. If it is a positive number, that will be healthy case. If it is a negative number, that will be a faulty case. So like this, the trained model will help you to clearly classify the two cases. Cases are healthy and faulty. Understood? So there are many algorithms available to optimize the case, maximizing the margin and minimizing the error, mean error, prediction error. So using which you derive the model. Using the trained model, you can definitely predict the condition. Understand what I am telling? Yeah. So this is the message I want to convey. So you can do research on the classification algorithm. What I have just explained is SVM based algorithm. And then you can also research on the precursors, method of accessing the precursor, and identifying the fault, predicting the fault well in advance, right? So I hope I have delivered enough to start a research in this area, condition monitoring, real-time condition monitoring, which is a very much required area, or very much huge requirement is existing in the market towards the improvement of reliability and availability of the system, electronic system in general, and hence lot of scope for research is still existing, especially when we are talking about all electric vehicles and we want to convert all the IC engine based vehicles to electric, purely electric vehicles, right? So lot of opportunities are there, challenges are there. So jump into the area, do research and come out with a feasible solution, engineering solution. So any doubts you are having? If you are having any doubts, you can ask me. Otherwise, we will stop the presentation or class for the day. Hope that conveys a possible area for research for each one of you. Right?
Yes, sir. Yes, sir.
Yeah. So thank you for your patient hearing. Thank you to the organizers for inviting me to this session. Okay.
Thank you so much, sir. If there are any questions or queries from the participant side, they may post them in the chat box.
I think we can conclude.
Yes, sir. So I believe there are no questions. Thank you so much, sir, for the session. It was really, really good and informative. I'm sure all of the attendees had a real fruitful time. I, on behalf of the entire organizing committee of this faculty development program, and on my own behalf, I'd like to wholeheartedly thank you, sir, for the session. Thank you so much. And I extend a very hearty vote of thanks to all the attendees present here. This is the faculty development program on embedded system and machine learning for engineering application organized by the Department of Electrical and Electronics Engineering, TKM College of Engineering, in collaboration with University of Technology, Brunei. With this, we are winding up for the day. Thank you so much.
Thank you.
So before that, as a fact of appreciation, inviting Mubaris to present a virtual memento to you, sir.
Yeah, thank you. Thank you,
Thank you,
for the memento. Okay. Shall I leave?
Yes, sir. Yes, sir.
Okay.
Thank you.
Thank you.
Thank you. So today's session is over. Tomorrow we can have only one section, that is morning section. After that we can have Alpri function. So all of you are requested to join in correct time, that is exactly 9:30 a.m. Thank you all.